Good morning everyone. Here I am going to record in the continuation of the previous lecture, lecture number 7 on carrier mobility. So in the previous lectures we have defined Schrodinger wave equation, the physics of the semiconductors, the drift and the diffusion currents, and some basics of how the energy band gaps will be in the case of the intrinsic and extrinsic semiconductors. So in this lecture we see how the carrier mobility will goes on, keeps on increasing and decreasing in the case of the N type or P type semiconductors. So what is carrier mobility? So basically mobility, the age at which a carrier electron or hole moves in a semiconductors. So how the electrons and holes are moved in a particular semiconductor in a N type or a P type semiconductor, this defines the mobility. So in the last classes we have defined drift current and the diffusion current. So as we have already discussed that what is drift current. So drift current is the mobility of the carrier under the influence of the electric field, and on the other hand diffusion current is defined as the diffusion of the or the mobility of the carrier from high concentration to low concentration. So here we define a symbol which is mu n for the case of the electrons and mu p for the case of the holes for the mobility. So here drift velocity is defined the speed at which a carrier moves in a crystal when an electric field is present. So here Vd is equivalent to mu n e for the case of the electrons, and similarly for the holes we have Vd is equivalent to mu pe. So as we see that Vd is directly proportional to electric field and Vd is directly proportional to the mobility of the electrons. Similarly for holes, Vd is directly proportional to electric field and Vd is directly proportional to the mobility of the holes in the valence band. So this carrier mobility is connected with the conductivity and carrier concentration also. So here there is a relationship between conductivity sigma and carrier concentration n and mobility mu. So here sigma is defined as the conductivity, how the current will be conduct in a particular semiconductor due to the movement of the charge carriers in the semiconductor. Either it can be a p type semiconductor or a n type semiconductor, extrinsic type. So here the conductivity sigma is directly proportional to mu, which is sigma is equivalent to n e mu, where E is the electron charge, or you can say Q, which is 1.6 into 10 to the power minus 19. Small n is the number of electrons here, and mu is the mobility of the charge carrier. So mu can be mu n or mu p. According to that we can define the conductivity in the valence band or in the conduction band, or you can say conductivity for the electrons or for the holes. Similarly, so we can write it like this: sigma n is equivalent to n e mu n and sigma p is equivalent to n e mu p. So these are two equations for the first one is for the electrons and the second one is for the holes. So in the semiconductors, as we know that the conduction band has more number of electrons and the valence band has lesser number of electrons, as there will be a population inversion occurs. So in that case the mobility of the charge carriers sigma n or conductivity is defined in terms of mobility, which is n e mu n or n e mu p, where E is equivalent to 1.6 into 10 to the power minus 19. So here there is another term which is called resistivity. So resistivity is basically rho and it is related with the conductivity, and resistivity is inversely proportional to conductivity. So wherever there is a conductivity, there is always a resistivity there or resistance is there. So obviously the movement of the charge carriers is not as it will flow from higher concentration to low concentration all the electrons. So there will be some hindrance into it also. So that will give you the value of the resistivity. So as we have the larger number of conductivity, we have reduced value of the resistivity. So mobility is average velocity. Basically it's a kind of a velocity, how much the carrier will drift or diffuse from one position to another position or from one part to another part of the semiconductor lattice. So mobility is the average velocity, which is defined as V and it is in centimeter per second, which is introduced by electric field E, which is also in volts per centimeter, and expressed by this relation, which is V is equivalent to mu into E. So we have V is directly proportional to E. So we can define Vd, that is the drift velocity, which is mu into E, or in the drifting case we have the velocity is directly proportional to charge carriers also. So next we have What is resistivity? So resistivity is a property of the semiconductor or a conductor. Every material has a resistivity. It is actually the resistance of a 1 meter long piece of wire line having a cross sectional area of 1 meter square. So resistivity is defined in terms of a, suppose a wire line, and it has a very long 1 meter line, and it has a cross sectional area of 1 meter square. So in this case the resistivity is around 1. So as you imagine, this is always a very low number. So for copper, the resistivity, as copper is a metal, the resistivity, because it has a high conductivity, the resistivity obviously it is very low. So rho is equivalent to 1.72 into 10 to the power minus 8 for the case of the copper. So here we define rho is equivalent to RA by L, and the unit is in ohm meter. So resistivity of semiconductors, how the semiconductors are different from metals and insulators, we have already discussed according to the energy band gap, and how the doping will increase the conductivity in the semiconductors. We have another thing, that semiconductors and insulators and conductors have different values of the resistivity. As we can see from the table, that insulator has a resistivity around greater than 10 to the power 8 ohm per centimeter. Obviously insulator have less conductivity and more resistivity is there. Similarly for semiconductor, it is 10 to the power 8 ohm centimeter to 10 to the power minus 3 ohm centimeter, means it is greater than 10 to the power minus 3 and less than 10 to the power 8. It has a wide range of the resistivity, or obviously the wide range of the conductivity is there. Similarly for the conductors, we have resistivity that is around 10 to the power minus 3 ohm centimeter. So there are some elements like silicon, germanium, which are the elemental semiconductor. These are elemental semiconductors. So silicon and germanium are, which we have already discussed, that these are elemental semiconductors. These are the purest form of the semiconductors. The fourth and fifth group elements are there, that is silicon carbide and all. And then third and fifth group elements are there, that is aluminum arsenide, aluminum antimony, gallium arsenide, gallium phosphide, gallium antimony, indium arsenide, indium phosphide and indium antimony. These are the some compounds for the third and fifth group element. Then there are some compounds for the second and sixth group element, that is cadmium, selenium and cadmium tin and zinc and selenium, etc. And then for the fourth and the sixth group elements like tin and selenium, etc. So the resistivity of the semiconductor is generally sensitive to temperature. It is very much sensitive to temperature. As you increase the temperature or doping concentration, the resistivity or the conductivity will change. So it is sensitive to temperature, illumination, magnetic field and minute amount of the impurity atoms. So as you increase the doping in the semiconductors, the conductivity will change, the conductivity will get increased and also the resistivity will get reduced. So we can alter the conductivity and the resistivity of the semiconductor in a particular way. So you can see from this figure that increasing resistivity from copper to glass, we have a glass here, silicon here, germanium here and then copper. Then the copper has a very less resistivity, which is 10 to the power minus 6 because it is a conductor. Then germanium and silicon has in between 10 to the power minus 3 to 10 to the power 3. And then glass, which is silica or the gallium arsenide, we can use. So it has a resistivity around 10 to the power 6. So it has a more resistivity as compared to the copper. So we have this increasing conductivity from left to right, and from right to left it is increasing resistivity. So resistivity of a typical semiconductor is shown in this figure, particular figure, and we can easily differentiate between how the metals and the semiconductors are different in terms of their resistivity and conductivity. So this is the table of material versus resistivity versus temperature coefficient. We have a list of conductors here: silver, copper, gold, aluminium, tungsten, iron, platinum, mercury, nichrome. Similarly, the resistivity values for these conductors are there. For silver, it is 1.59 into 10 to the power minus 8. For copper, it is 1.68 into 10 to the power minus 8. So as you can see that there is a difference between conductors and semiconductor. In the case of the semiconductor, if we want to see, that is for carbon, we have 3 to 60 into 10 to the power minus 5, and for germanium it is 1 to 500 into 10 to the power minus 3, and for silicon it is 0.1 to 60. So it has a variation in the resistivity from conductors to semiconductors. On the other hand, in the case of the insulator, it has very high resistivity, that is around 10 to the power 9 to 10 to the power 12. So you can see that glass has a resistivity around 10 to the power 9 to 10 to the power 12, and hard rubber has a resistivity around 10 power 13 to 10 power 15. This is the temperature coefficient for the conductors case, and then for the semiconductors, and then for the insulators. So we can see easily that the temperature coefficient here alpha is 0.0061 for the silver, but for the case of the germanium it is minus 0.05. So as we increase the temperature, the variation in the resistivity and the coefficient is keeps on changing for the case of the conductors, and then semiconductors, and then for insulators. So we can define conductivity. It is defined as the ability of the charge carrier to pass through them. So here from this diagram I want to show you that suppose there is a particular lattice structure, and we have to apply a voltage here from positive to terminal is connected with the positive side, and the negative is connected to the negative side. So the electric field is in the movement from positive to negative side, and the electron will flow from negative to positive side, and the whole movement is obviously opposite to the electron flow. So basically what amount of current is flowing in this particular conductor is defined your conductivity. So it is defined as the ability of the charge carrier to allow the current to flow in a particular conductor or a semiconductor or an insulator. Obviously insulator doesn't have so much of conductivity. So we have the case of the conductors, or we have the case of the semiconductors. So this is the conductivity equation sigma, and sigma is defined as 1 by rho basically, and it is defined as NQ mu, where mu is the mobility of the charge carriers. So here N is the number of electrons, and Q is the 1.6 into 10 power minus 19. So with this formula we can find out what is the value of the conductivity for a particular semiconductor. So sigma define the conductivity. Obviously sigma is equivalent to 1 by rho, and from here we can define rho, which is 1 by sigma. So that is the inverse of the particular conductivity. So resistivity is the inverse of the conductivity, and we define these equations here for the case of the semiconductors. So now we have conductivity of N type and P type intrinsic type of semiconductors. So we have already discussed about intrinsic and extrinsic semiconductors. As we have discussed that intrinsic semiconductors are the purest form of the semiconductors. On the other hand, extrinsic are those in which we implant impurities or dope some impurities in the form of the third group elements or the fifth group elements. So for intrinsic semiconductors, we have sigma I is equivalent to Q multiplied by N mu N plus P mu P. So sigma is defined as Q N mu N. So here mu N is the mobility of the electrons, and similarly mu P is the mobility of the holes. So this is the mobility of the electrons in the conduction band, and this is the mobility of the holes in the valence band. And Q is the electron charge. So for N type semiconductors, we have number of electrons much larger as compared to number of holes. So we have Q is equivalent to Qn. We can avoid this term, that is Q into P into mu P, and we have sigma, which is approximately equal to Qn mu N. For P type semiconductor, we have number of holes is much greater than number of electrons, and for this case we have sigma, which is equivalent to Qp mu P. So this is the equation for N type or P type extrinsic semiconductors. We implant some impurities into it, and it will get into change in the conductivity of the semiconductors. So now the next is the conductivity equation for P type. So sigma is, we have already discussed, sigma is NQ mu E and plus PQ mu N. So sigma is defined for the P type is PQ mu N or mu H. You can have the mobility of the holes. So here sigma is conductivity, P is the positive carrier density, Q is the electric charge, and mu H is the electron hole mobility. So we have electron hole mobility in terms of meters square per second. Charge has a value of 1.6 into 10 power minus 19. Similarly, the conductivity equation for N type, we have extrinsic semiconductors N type, where N is very much greater than P, and sigma is equivalent to NQ mu E plus PQ mu H. And obviously it will results you sigma is equivalent to only NQ mu E for the case of the N type of extrinsic semiconductors. So sigma is the conductivity, and here is the negative charge carrier density. Q is the electric charge, which is same as earlier, that is 1.6 into 10 power minus 19, and mu E is the mobility of the electrons in this case for the extrinsic semiconductors. So this is the table showing the band gap conductivity versus mobility. Here there are materials in the first line, that is silicon, germanium, and the second type of materials, which are, these are called elemental semiconductors. So these are elemental, and now these are the third and fifth group elements, and these are the second and fourth group elements. So there are some categories of material here I am showing on the table. That is, in the left side we have silicon, germanium, which is the elemental semiconductors. Then we have third and fifth group elements, which is gallium phosphide, gallium arsenide, indium phosphide, and then second and fourth group elements, which is cadmium, selenium, and zinc, tellurium. So for these materials we have different band gaps. So for silicon and germanium, we have silicon has a band gap of 1.11 and germanium has a band gap of 0.67. Similarly, for gallium phosphide, it has a band gap of 2.25. Gallium arsenide, it has a band gap around 1.42. Similarly, cadmium, selenium, it has a band gap of 2.40. So we have electrical conductivity in terms of these band gaps. So sigma, value of the sigma here is, for the silicon and germanium, it is obviously, it is the purest form of the semiconductor. So 4 into 10 power minus 4 and 2.2, it has higher value as compared to the third and fifth group elements when you doped some thing. So obviously in the gallium arsenide, it is 10 to the power minus 6, and then indium antimony, it has it 2 into 10 to the power 4. So similarly, we have the electron mobility for silicon and germanium. The electron mobility for silicon is 0.14, then for germanium is 0.38. Gallium phosphide has a mobility for 0.03, then gallium arsenide 0.85, then indium antimony, that is 7.7. Similarly, hole mobility, we have 0.05, which is for the case of the silicon, and then 0.18, which is the case for the germanium. And then for gallium phosphide, gallium arsenide, and indium antimony, which is 0.015, then 0.04 and 0.0. So this table basically gives you an idea about how the band gaps will vary from one material to another material, whether it is an elemental semiconductors or a third, fifth group or a second, fourth group elements, and how their conductivity will keeps on changing from the elemental to compound semiconductors and the mobilities. And you can find out easily the value of sigma, which is n q mu n for the case of the electrons, or sigma, which is p q mu p for the case of the holes. By these two equations, we can easily find out the value of the conductivity here. So next we have resistivity and sheet resistance. So we have the resistivity, already we have discussed that sigma is equivalent to conductivity, and resistivity is the inverse of the conductivity. So electrical resistivity is defined as rho, and it is equivalent to 1 upon sigma, and it is equivalent to 1 upon qn mu n plus qp mu p, as we have sigma is qn mu n plus qp mu p. So we have the resistivity rho is 1 upon sigma. And similarly, the sheet resistance for this, suppose we have a homogeneously doped sample, which has having a length of L, thickness of T, and a width of W, and we apply some voltage, positive voltage, to one end, and another is connected with a negative terminal. So we have a current flow from positive to negative, and there will be a sheet resistance R, which is given by rho L upon WT, or RS L by W, where when L is equivalent to W, length is equivalent to width. In that case, RS is equivalent to, the sheet resistance will be calculated, and in that case sheet resistance will be equivalent to rho by T. So by this way we can find out the sheet resistance for a homogeneously doped sample. So there are some methods of measuring sheet resistance. So first method is known as two probe method. Here the voltage and current is measured on the two sides of the, as the name suggests that it is a two probe method. So the voltage and current is measured on the two sides of the conducting bar to calculate the resistance. So here we can see from the figure, the first figure, A figure, shows there is a conducting bar, and there is a voltage, voltmeter, and a current, that is a ammeter here. So this is the ammeter and this is a voltmeter, and we just measure the value of the voltmeter and the current with the voltage and current at the two sides of the particular bar. Similarly, we have four probe method. Here the voltage and currents are measured on the 4 points of the bar to calculate its resistance. So we have 4 points here, and we just calculate with the inner sides and the outer side the voltmeter voltage and the current measurement in a particular sheet resistance or a particular block. So with these two methods we can easily find out the value of the sheet resistance. So the last method is the third method, which is called as electrode method. Here a conducting bar is placed in between the two electrodes, and so that resistance can be calculated across it. Guard rings are here provided to used to protect the conducting bar from external environment. So here there is a G1 and G2, the guard rings are there, and we calculate the value of voltage and the current to find out what is the value of the voltage and current in the particular specimen sheet. So T defines the thickness of the conducting bar here, and D2 is the length of the particular specimen, and there are two electrodes, upper electrode and the guard ring are there provided in the particular specimen sheet. So there are some design of resistors. What's the resistor? The resistor is a component in a circuit to reduce the flow of the current, electric current. So it is a symbol which is defined by this symbol, resistance, in a circuit diagram. So resistance value is calculated in ohm, we all know, and it's a famous law, that is V is equivalent to IR, or which is called as Ohm's law. So here there is a triangular method by which we can find out the value of the V. If we know two parameters, that is IR, we can easily find out the value of V, or similarly we can find out the value of R. If we know the value of V and R, similarly we can find out the value of R if we know the value of V and I. So this is about the design of resistors. So now the classifications of resistors. So we have various long classification of resistor. So resistors is classified into two types. First one is the linear resistors and the second one is the non-linear resistors. So in the linear resistors we have fixed resistors, a variable resistors, and the non-linear resistors have a categories like thermistors, photoresistors, varistors, surface mount, etc. So what is called as linear resistors? In the linear resistors, the current and voltage can be measured in a linear manner. So here the current and voltage measurement should be in the linear manner. In the non-linear resistor, we have the current and voltage changes in non-linear manner. In the fixed value of resistor, value of resistance will never change once it is designed or it is fixed to a particular circuitry. In the case of the variable resistor, we can alter the position of the value of the resistor, or with the knob we can change the value of the resistor in a particular circuit. In the thermistor, value of resistance will change as the temperature will change. So if we increase or decrease the temperature, the value of the resistor will change. Automatically it will change in a particular circuit. So according to the application, we can take the value of the resistor. If we want a lesser value of resistor or a higher value of resistor, as in the practical cases, we can use thermistors also and variable resistors also. Next is the photoresistors. So value of resistors changes as the light falls on the surface. So the photoresistors, as a term defined, it is something like a photo. So whenever the light is incident on a particular resistor, the value of the resistors changes. Next is the varistors. So variable resistors value will change randomly. So varistor have a variable resistor and the value obviously changes with random, and it has the same thing like a variable resistor, thermistor. The varistor is the same thing. Next is the surface mount device. So value of resistance is calculated on the surface of the device. So on suppose there is a particular lattice and we have to implant some sheet over the lattice, and we have to calculate the resistance value. So value of the resistance is calculated on the surface of the device. These are some categories of resistors we can use according to our applications, that how we want the voltage and current to be measured in a linear manner, so we use a linear resistor. If we want to measure voltage and current in a non-linear manner, we use non-linear resistor. If we don't want to change the value of the resistor, we use fixed type of resistor in a circuit. If we want to particularly tune the value of the resistor, we use the variable resistor. Then thermistor, where the value of resistance will change as the temperature will change. Then next we have photoresistors, wherever the light falls on a particular surface of the semiconductor device, the resistance value will keeps on changing. So, if we connect on the load the resistance and the light is falling on the particular source, then there will be a change in the resistance value. Then next is the varistor, which is the variable resistor, where the value will change randomly. It will change randomly, not we are not able to tune the value of the resistor, it will change automatically. Then last one is the surface mount device, where we uh, change the value of the resistance or calculate the value of the resistance on the surface of the device. So, these are some classifications of resistors. So, next is the measurement of resistor. We all know the color code for the resistors, and we easily define there are some coding methods for getting the value of the how much the resistance value we are using in a particular circuitry. So, there are 4 bands resistor, looser tolerance, and the 5 band resistors are also, which has a narrower tolerance. Similarly, we have 560 ohm with plus minus 10% tolerance and 237 ohm with plus minus 1% tolerance. So, we have these colors in the resistors. If you see the resistor, there are bands of these colors like black, brown, red, orange, yellow, green, blue, violet, grey, white, gold and silver. And in the first band, we assign these values 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Similarly, if it has a in the second band, it has the same value. Third band, it has the same value, but has some multiplier into it. So, black has a multiplier of 1 ohm. Similarly, brown has a multiplier of 10 ohm. Then red has a multiplier of 100 ohm. Then orange has a multiplier of 1 kilo ohm. Then yellow has a multiplier of 10 kilo ohm. Then 100 kilo ohm. Similarly, for blue, it is 1 mega ohm. Then violet, it is 10 mega ohm. Then for gold and silver, it is something different, which is 0.1 ohm and 0.01 ohm. There will be a tolerance level for each of these bands, that is plus minus 1%, plus minus 2%, 5%, 25%, 1%, 0.1% and 0.05% for the violet and the grey. And for the gold and silver, it is 5% and 10%. So, according to these color coding methods, we can easily find out the value of the resistance. So, we see whatever the band is there in the resistance, it is black, brown, red, orange. According to that, first band, if it is black, then we take the value 0 into 1 ohm. If it is red in the second band, we take the value of 2 into 100 ohm. Then third band, we take the value of the 2 into 100 ohm and so on, and we keeps on taking the tolerance level also and calculate the value of the resistor. So, in this lecture, what we have discussed about, we have discussed various parts of the resistivity, conductivity, as we have already discussed the drift velocity and the diffusion velocity in the last lectures. So, in the continuation of this lecture, we see how the mobility of the drifting and the diffusion currents will change, keeps on changing as we increase the temperature, how the variation of the mobility in the electrons and the holes in the conduction band and in the valence band keeps on changing. We see through the table that how the number concentration is there keeps on changing, and how the mobility or the conductivity values change from elemental semiconductor to third, fifth group elements, then to second and fourth group elements. So, earlier we have seen the drift and the diffusion current equations, which are known as carrier transport equations. So, we use these equations to implement various applications of in the semiconductors area, in the semiconductors physics. In the next lecture, we see how the Fermi levels are, actually we have seen the Fermi level position in the conduction band and in the valence band. In the case of N and P type extrinsic semiconductors, we have seen that already that the Fermi level just below the conduction band in the N type semiconductor and just above the valence band in the P type semiconductors, we particular can calculate the value of the occupancy of electrons in a semiconductor in a by the help of the Fermi direct distribution function. So, in the next lecture, we are going to see about how the these conductivity equations and resistivity equations is helpful in carrier transport equation, and how we can use it in numerical problems, how you solve some of the numericals based on Fermi level position and occupancy of electrons and holes. We also see the Fermi direct distribution function, that how the probability of particular state to be filled by an electron and holes is to be defined for a different values of E minus EF, or if suppose E minus EF has a value of kT and suppose E minus EF has a value of 3 kT, or E minus EF has a value of 10 kT, and what is the value of the Fermi direct distribution, that is the probability of electron is there in the particular state. So, we see all these in the next lecture, lecture number 8. So, suppose I think you have not any doubt on this. If you have any doubt on this, we can just discuss in the next lecture with some numerical problems. Thank you so much.